In this video, we're going to look at some multiple choice questions and just some more Converge and Diverge series examples. So first of all, this is from the 2014 International Exam. It was number 24. It says, which of the following series converge? Well, they are, let's start with this one. This is alternating, of course, and it's just 1, negative 1, 1. Now, converge, remember, means that the sum is approaching one number. Okay, to be convergent, this means the sum is approaching one value. It has essentially a limit. Okay, so this 1 plus negative 1 plus 1, this is bouncing back and forth between 1 and 0. So this is not approaching one value. It's bouncing between two. So that does not converge. Okay, now the next one, 1 plus 1/3 plus 1/5, 1 over 2n minus 1, well, it isn't alternating, it's all positive, and think about, this is the general term they're giving us, so it's essentially this series. Well, if you think about it like it's like you could maybe do a limit comparison with it and compare it to, let me put limit comparison, compare it to 1 over 2n, which is a divergent p-series, because it's a constant over n, and the n to a power, and the power is not greater than 1. If you do limit comparison, you find out that this also diverges. Well, this next one, again, you kind of look at this general term, and you bring this over and say, well, it's like saying this, which is the same as that, 3 to the negative 1, which is the same as this. I'm just going to keep going with simplifying. You probably see where I'm going, but that is a convergent geometric series. So the only one that converges is 3. The first one doesn't approach one number. The second one, by limit comparison, would not converge. And the last one is a convergent geometric. Okay, let's look at another one. This is also from last year. It says, what's the sum of the series? Okay, well, of course, if we're being asked to find the sum, we know it has to be geometric. We have to know that formula. It's first term over 1 minus the rate. And maybe it helps you to take this and bring it down and say, well, it's negative 2 raised to the n, and it's e to the n times e. Right? Because that's e to the n plus 1. And why I think that's helpful is now we got things all raised to the n. We could take this e as a constant and kind of bring it out front and have 1 over e multiplied by negative 2 over e to the n. Take the stuff that's to the nth power and put that together. So now if I plug in 1, because that should give me the first term, I have negative 2 over e to the first times 1 over e. Okay, so the first term, a, would be 1 over e times negative 2 over e, or negative 2 over e squared. Okay. The next would be the ratio. Well, that's whatever's being raised to the n. That's just negative 2 over n. So my formula is going to be, sum would be negative 2 over e squared multiplied by 1 minus negative 2 over e. So that's going to be negative 2 over e squared over 1 plus 2 over e. Now, you can kind of do some algebra here, and you could say, well, negative 2, we could put this e squared and then have 1 plus 2e, 2 over e, excuse me. So we should have an e squared multiplied by 2 over e. So I'm looking for a negative 2 on top, and then an e squared plus 2e, if you multiply that e squared in. So it is b. Okay, so a lot of algebra goes into this. Do not forget this geometric sum formula. I think it's helpful to start by rewriting it in kind of a nice form where it's a constant, and then all the stuff that's to the n is together. Then get your first term and your ratio, and then it's just algebra. We have the first term over 1 minus the ratio. Now, having this 2 over e squared, you can drop this into the denominator and make it multiply through, and it cleans up pretty quick. Okay, let's look at just some converge, diverge problems. Now I'm going to go through these pretty quickly and just kind of talk about the test I would use and whether it converges or diverges. And let me kind of go through this in the order that I usually look for things. I start by looking for things that are geometric. Remember, geometric means it's a number raised to the nth power. So let's start going through these. This has a number raised to the nth power, and you could rewrite it as 5 multiplied by 1/7 to the n. What's being raised to the nth is less than 1, so it converges. Okay, let's see if there are any more like that. That's always the thing I start with looking for. This is it to an n, but we also have other things. So, here's something, a number to the nth power, but this number is not less than 1. It's not between -1 and 1, so this diverges. Okay, let's keep going. Down here, going along. Now this, a number to the n, a number to the n, I could rewrite. I could rewrite this as 3 to the n over 2 squared to the n, which is the same as 3 to the n over 4 to the n, which is 3/4 to the n, and that converges. Okay, so even though it looked a little different, we were able to do it kind of the same way. The next thing I look for are p-series. P-series are where you have a constant on top and n to a power on the bottom. And you'll converge as long as that power is greater than 1. So we start off here right away. We have a constant, n to a power. This power is greater than 1, so this converges. Okay, we keep on going. I don't see that anymore here. I don't see that anymore here. Here we do. We have a constant, and then it's a root, but we could rewrite the 5th root as n to the 1/5. We should rewrite roots with powers. Well, that power is not greater than 1, so this diverges. Okay? Probably my next test that I would look for is maybe even root test. Root test, remember, is looking for a function raised to the nth. So the difference between it and geometric is looking for a number to the nth, whereas root test looks for a function to the nth. So nothing on the top row is like that, but here right away we have a function raised to the nth power. And again, what we look for then is what's inside here. Does this have a limit less than 1? And it does, because the limit would be 2/5. So it's kind of like saying 2/5 raised to the nth power. Well, 2/5 raised to the nth converges. Okay, I think that's the only one like that. So then I would move on to the limit comparison test. Limit comparison is great for when you have a polynomial on top and a polynomial on the bottom, like something with just n's to powers over something with n's to powers. So, like this first one, if I instead of the third one over here, we have 2n plus 1, and this looks ugly, but I could rewrite this as n to the 5/2. So we use our highest powers. We say, well, it's 2n over n to the 5/2, which is 2 over n to the 3/2. This is a convergent p-series that we're comparing to. And I don't have the room, and I'm not going to take the time, but remember, limit comparison says we should take our original series, divide it by our comparison series, and as long as we get an answer greater than 0, we have agreement between our two series. So whatever our comparison series does, so does this series. Well, our comparison converged. This will converge as well. This test will also work for the one next to it because it's n to a power, n to the power. So take the highest powered stuff, n over n to the 3/2, which reduces to 1 over n to the 1/2. Well, that's a divergent p-series. And again, if you actually went through it and did the original divided by the comparison, you would get a limit greater than 0, so they agree, and this diverges. Going down here to this problem, this one actually you could do by the nth term test. You could spot, I hope right away, that this has a limit of 6/7. So if I just keep adding 6/7 over and over and over again, I'm going to diverge. But you could also do this kind of with limit comparison. You could take the high-powered stuff and say, well, I just get 6/7. There's no ends in that. So that's just adding 6/7 over and over and over and over again. Obviously, this diverges by the nth term test. And if you took the original and divided by the comparison, you would get a limit greater than 1, so you have agreement. This diverges as well. My next test would be ratio test. Remember, ratio test says you take the next term and divide it by the term you're on, and you should get a limit of less than 0 if it converges, greater than 0 if it diverges. So for example, this first one that's left, so this one, and it's a great ratio test. Ratio, I look for a mix of things. Factorials with exponents. Exponents with polynomials. That's kind of what you look for. So when you have a mix of things, like these problems right here, okay, this one and this bottom one. So we take the next and divide it by the term we're on. I'm going to just multiply by the reciprocal, and we find the limit. I don't have a lot of room, so I'm going to, this cancels with that, and I have a 3 on top. N factorial over n plus 1 factorial leaves me with just 3 over n plus 1, and the limit of that is 0, which is definitely less than 1, so this converges. Okay, we're looking for a limit less than 0 to converge, greater than 0 diverges. This one, if you did 2 n plus 1 factorial over e to the n plus 1 multiplied by e to the n over 2n factorial, well, the e's are easy enough. The n factorial goes with that, but we end up, the 2's I guess cancel too. We end up taking the limit of n plus 1 over e. Well, infinity over e is infinity. That's obviously greater than 1, so this diverges. Now we only have one left, and it kind of doesn't fit into any of the others. The test I would use for this is direct comparison, and that's really because it's all that's left. For direct comparison, I would compare to something like 1 over n cubed, which is convergent p-series. And I would just say, well, sine is a maximum of 1. Sine will never be greater than 1, so most of the time it's less than this convergent p-series. It's occasionally equal to this series, but most of the time it's less. So if it's less than a convergent series, it must converge as well.